the idea today is to have a little bit of an introduction to radio astronomy. So we've done a lot of optical astronomy already, but I'm a radio astronomer really by training. And so I'm much happier. I wanted to make sure we did a little bit of radio astronomy in this class. So this is a fun slide for me. This is me at lots of different radio telescopes. Okay, so we're going to start with some definitions about what radio astronomy is. So I think you might have seen this before, but this is a sort of astronomer's view of the electromagnetic spectrum in terms of what makes it down to the ground. So this has the wavelength along the x-axis going from gamma rays and x-rays over a very short wavelength over to the radio part of the spectrum over here at very long wavelengths, so into the sort of meters, centimeters, meters scale wavelengths. It also has the frequency. We tend to use them interchangeably, so just have to get used to that. And then the y-axis is supposed to show the atmospheric opacity. So it shows the basically 1 minus the % of the light of that wavelength that reaches it to the ground, right? So we all know, luckily for us, the atmosphere is opaque to gamma rays and x-rays. It starts to dip in the UV. It dips quite a long way in the optical, but not to zero. So not everything gets through. We know that, especially on cloudy nights, right? Then there's a whole lot of mess in the infrared until you actually get a patch where properly in the infrared you can't see anything from the ground. You have to go into space. But then we have this beautiful wide gap here that we call the radio part of the spectrum. It's actually very broad compared to optical, right? So it's really a large range of wavelengths. And the atmospheric opacity is basically 0%. Basically everything gets to the ground. And even through clouds, even through snow. So you can do radio astronomy in all kinds of horrible weather, and that we wouldn't think of being able to do astronomy in. That's not true at the very shortest wavelengths. You can start to see this stuff peaking up as water molecules start to get excited by radio waves. And then at the very, very longest waves, we have an ionosphere around the Earth. So there's actually charged particles in the upper atmosphere, and the very longest wavelengths interact with that and don't pass through the atmosphere. And so if we want to do extremely long wavelengths, we'll have to go into space again. Okay, so the sky would look really different in radio astronomy. So this is an image of the radio sky, showing, you can still see some stuff that looks a bit similar. You can still sort of see dots that look a bit like stars, but there's also these very big circles and blobs and structures that are radio objects in the Milky Way. So this is actually a strip around the entire sky now that's been sort of pasted into a straight line, right? So this is the sort of the classic view of the Milky Way in optical, where you can see the dust lanes and the bulge of the Milky Way. But these top three here are all radio views of the Milky Way, all different parts of the radio spectrum or ways of doing radio astronomy that get us at different physical properties of the Milky Way. We can probe different things. We can probe different physical mechanisms that make light, that make this electromagnetic radiation by looking at it in different wavelengths. So there's three main categories, or there's three categories of radio emission that's created by objects in the sky. Thermal emission will make radio waves, right? So this is the classic black body spectrum, right? That's a very broad spectrum that goes right across the electromagnetic spectrum. And so some of it will be in the radio part of the spectrum. So this is your black body spectrum, the classic one. The sort of luminosity is 4 pi r squared sigma t to the 4th thing that I go on about a lot in ASTRH 204 and 205. And there's two regimes where there's an approximate thing for it. There's the Wien's law, which is good at the high frequencies. And then there's the Rayleigh-Jeans relationship, which is, this is the approximation. So the brightness is just proportional to the temperature. So if you increase the temperature of the object you're looking at, the Rayleigh-Jeans brightness, just like if you double the temperature, you get twice as much power. So here's a nice plot that it's a little bit low resolution, sorry about that, kind of highlighting this radio regime all of these lines basically are parallel. So these are the lines of different temperatures. You remember the peak moves over to lower wavelengths, to higher frequencies, shorter wavelengths as the temperature increases, but that low frequency slope is always just, they're always just parallel to each other. So this turns out to be super useful for radio astronomy, which we'll come back to. But we're always in this regime in radio astronomy, even for the coolest objects that we detect. Okay, so because that's that's the radiation that objects make because they have a temperature, we call that thermal emission. And then we will contrast that to non-thermal sources of emission. So radio waves can be made by electrons, which are accelerated in different ways. So there's two kind of main ways this happens. There's the free acceleration. So it has that fancy German name, Bremsstrahlung, where you have an electron that interacts with a positive charged particle and it changes direction. And that change of direction, it releases a photon. So those of you who have taken advanced E&M or who are intending to, I would assume that you would do the calculations for Bremsstrahlung in that class. It's not important for this class to be able to do those calculations, but just to say I'm not going to do them here. Then we also have synchrotron or cyclotron. So for this, you also need a magnetic field, and you have charged particles that have basically a spiraling path around the magnetic field because of the way forces work with moving charged particles in magnetic fields. And again, that spiraling is acceleration, and so photons are created. The only difference between synchrotron and cyclotron is the speed of the electrons. So cyclotron ones are going at moderate speeds. Synchrotron are going very, very, very high speeds. And then there's various spectral lines. So this is sort of thinking back to quantum mechanics, right? Energy transitions can create photons, and sometimes those photons are in the radio part of the spectrum. Turns out we actually have both atomic and molecular lines in the radio parts of the spectrum, which I'll come back to. But before we come back to that, let's have a look at non-thermal emission. Accelerated charged particles radiate. And so you can calculate things like the power per solid angle if you want to from your E&M textbook, but we're not going to do it here. Yes, that's right. So if you take a graduate E&M class, you might end up being asked to calculate the emission from a population of accelerating electrons. So you'll have electrons with a range of velocities going through your magnetic field, and you can calculate what the spectrum of the emission would be. That's the thing I remember doing. Well, we're not going to do that here. It's way beyond the scope. Let's instead just look at what it turns out to be. So this is real data. The points here are real data, and the lines, I think, are models. This is a supernova remnant. And so this line here is a model for the Bremsstrahlung radiation. This is its thermal Rayleigh-Jeans, like that linear drop-off. And it looks like we're just getting the peak. And then the synchrotron radiation is usually a power law that's like the other way up to the Rayleigh-Jeans one. And you see, you need all of these to add up to kind of match the data. So this is the kind of thing people do, is they will take the sort of very broad spectrum of radio sources and try to fit the different components of the emission. I think the main thing to remember is just those three sources: thermal, non-thermal, which is accelerating electrons, and lines. Those are the three sources of radio emission. So the sun emits radio. So that's kind of cool. So here's a picture of the sun. You can just about make out the whole disk. So you can just about make out its thermal radiation. So again, way far down into the Rayleigh-Jeans part of the spectrum. And then you have these bright spots, which are associated with sunspots. So they look dark in the optical. I don't know if you remember, but sunspots have to do with magnetic field lines. And so we've got a plasma magnetic field lines. So we've got some kind of synchrotron radiation going on. So the sun is bright enough in radio to mess up quite a lot of radio astronomy observations. So you will see people favoring nighttime, although you can observe during the day. Okay, I'm kind of going to go out in distance because this is fun. Jupiter is a really cool radio source. So this is a kind of a picture of what's going on with Jupiter. But Jupiter has this huge ionosphere. It's an incredible magnetic field around the planet Jupiter. And because it has this moon Io, which has volcanoes, there's lots of charged particles in the magnetosphere of Jupiter. And so you can actually see it in this image. And so like the disk of Jupiter would be here in the center. But you're basically seeing the whole of this ionosphere and magnetosphere around the planet Jupiter. And it's also pretty variable. And so this is something that people do from relatively small antennas, look at the variability of Jupiter. You cannot make a picture like this, which, as we'll get to, the resolution is just way off. So you couldn't make a picture, but you can look at the time variability of it, which should be kind of interesting. I did have a spectrum because I thought it was nice that they had, again, the zoom thing is over the top of it for me. Okay, they had again picked out these different things, and I've forgotten what DAM, but you've got synchrotron and thermal adding up. That's going to bug me now. What's DIM and DAM? We'll have to look that up offline. I don't remember. I think it's something to do with the observations of Jupiter and like different time variability, possibly. So next, we have the Galactic Centre, which is very cool looking in radio. And I picked this picture out because it actually shows all kinds of different things in our galaxy that create radio emission. So this is the optical view of the Galactic Centre, and it's got various things marked. You've got the Sagittarius constellation. To me, it looks like a teapot, and then you've got the steam coming out of the spout of the teapot. That's a highly unofficial constellation story. But so, right, you vaguely remember, presumably, there's a supermassive black hole right here at the Galactic Centre. So there's all kinds of like high energy exotic stuff going on around that. And where has it gone? There it is. So that's the center of the galaxy, Sagittarius A star, or A. And you can see there's all this bright emission in the radio picture right around the center of the galaxy because there's lots of hot gas and stuff going on. But then you have other things you can see. So you can see these different kind of arcs and threads, supernova remnants. You can just about make out that they're circles. So again, we've got charged particles in the gas coming off of supernovae. So some of them really look like supernova remnants, a really big one. I think if there was anything else I wanted to point out, there's a background galaxy. So that would be a bright radio galaxy, like just way further away. And we only know it's further away because of the optical observations, probably not because of this observation. This is just like lots of bright radio emission towards the center of the galaxy. Okay, so I've got a better picture of a supernova remnant. This is really cool looking. So this is, I don't remember where this came from, but it's probably NREO. This is Cassiopeia A. So this is a supernova remnants in the Cassiopeia constellation. And you can see both synchrotron and thermal Bragg-Strahlung, so both of those mechanisms for non-thermal radio emission going on, and all of this different structure. This is big on the sky, but this would still be probably a very big radio telescope. So moving along on our tour of radio astronomy objects, we could not leave pulsars out. Some of you study pulsars, I know, when you're doing your research on pulsars. So this is something I learned. Radio emission mechanism for pulsars is actually not well understood, even though they were discovered in radio. So this is the discovery chart. So this is Jocelyn Bell's handwriting from the 6th of August, 1967. And this little fuzz here is the very first pulsar to have been discovered, which is at 19 hours and 19 minutes right ascension. So this is, this is pointing your radio telescope at a specific point in the sky is moving over it, and as something that causes radio emission passes through the sort of where you're looking at with your radio telescope, effectively, you see a signal and then it goes away. This is, as some of you know very well, but just to make sure we're all on the same page, this is the kind of physical model we have for what a pulsar is. So we have a neutron star with, again, a very strong magnetic field, and it has jets coming out of the north and south poles, so where it's rotating. Well, no, not necessarily where it's rotating, but it will have jets coming out of the north and south poles of the magnetic field, and those jets have charged electrons in them, so presumably some kind of acceleration of charged particles creating the radio emission. And if the magnetic field is at an angle to the rotation, you end up with this sort of lighthouse effect where the beam of radio emission passes through the Earth very quickly, sometimes as much as 1,000 times a second. So faster than your kitchen blender spins. This star, which is the size of a city, is spinning. And so we see them as post emission. So you, again, this is not an example of a time sequence, but often with pulsars, the data you're looking at is a time sequence. So it's like how much power as a function of time. Okay, so moving on and moving outwards, radio galaxies are a thing. And so some galaxies, if you look at them in radio, and this would be, usually it's like 6 centimeters, sometimes 20 centimeters, but this would be a continuum radio observation of very bright. The optical galaxy is probably, like a little small thing here in the center. You can find nice composite images sometimes. And they have these really extended jets that extend many times the size of the galaxy away from the center. They're often called 3C something, so you might wonder about that. And it comes from this 3C catalogue. So this was actually the 3rd Cambridge catalogue of radio objects in the sky. And this is the kind of data they came up with. This was the 1971 version. We have some of this data. We have actually transparent overlays that you overlay on those photographic prints. We have some of the data from this in the observatory library, which is fun sometimes to look at. So basically, they made a list of the brightest radio objects they could see. At the time, they really didn't know what most of them were. So they just basically numbered them. And so you have 3C and whatever is an object from this catalogue. It's a really standard way for astronomy to proceed. It's just to basically catalogue what you see. So if you think the Messier catalogue, some of you are doing the Messier marathon, right? Some of those are galaxies, some of them those are nebulae. Charles Messier, when he made that list, he was looking for comets, excuse me. And so he basically made a list of things that he didn't want to confuse with comets that didn't move. And it turns out that most of those are galaxies or planetary nebulae. So that was that Messier list, which is why it's kind of a mishmash of different things. The 3C catalogue is an equivalent of that in radio astronomy. So the Cambridge scientists went ahead and mapped the sky and made this catalogue of objects. So there's a bunch of basically radio galaxies that are usually called 3C something or other, and they have these big jets, and they're really big. This is one of those on the sky. I mean, they're big in angular scale, or they can be. So then we move on to my favorite bit of radio astronomy, the atomic 21 centimeter line. So this is a very, very low energy line in the ground state of neutral hydrogen. So you have a proton and electron in orbit around it, right? It's not actually in orbit, right? You know that from quantum mechanics. And there's 2 energy states that are, if the spin are aligned. So those of you who haven't taken quantum mechanics, you can think of spin as just like it literally spinning. It's not quite true because it's a quantum mechanics thing, but it is related to angular momentum. So there's 2 energies. So the spin is aligned or the spins are not aligned. They're in opposite directions. There's very, very small energy difference between them, which I know some of you have calculated, because I remember sitting in on Dan's class in quantum mechanics and having some people do this. So you can calculate that energy shift is equivalent to 1420 megahertz or 21 centimeters. This is very rare, right? This was never, I don't know if that's true. This is, at the time this was first detected in the sky, it had never been observed in the lab. You can never have atoms of hydrogen sitting around unaccosted for long enough to create this line. They form molecular hydrogen at any density we're able to create on Earth. They have to be incredibly low densities to be sitting around long enough as atoms. So the lifetime is 10 million years, another thing you can calculate in a quantum mechanics class. So they have to each individually sit around for 10 million years before they do this flip. However, 73% of all of the material in the universe that is detectable from electromagnetic radiation is hydrogen. So there's just tons of it out there. And so we see this everywhere in the sky. And this is a lot of my research has to do with detecting this in nearby galaxies. So here are some examples of what this looks like. So here is the optical galaxy is kind of the orangey bit here, and the pinky purple is the 21 centimeter radiation. So it's where this neutral hydrogen is. So we can tell from this that the stars in a galaxy are not most of what's there. We can tell that, you know, the neutral hydrogen, this gas, goes out to about twice as far from the center of the galaxy. This is really interesting for lots of different reasons. I mean, you get a better measure of the kind of the total mass of the galaxy from 21 centimeter, but also because it's way far out, if there's other nearby galaxies, it's the first thing that gets distorted. And so you get like tidal tails and all kinds of stuff going on. It's pretty cool. It's a line, so there's the Doppler shift. So you get a redshift right away from observing it, but also you can see how the galaxy is moving. So you can see the rotation inside the galaxy, which we can do in optical too, but 21 centimeters is a really nice way of doing it. And so this again is an image of a galaxy in 21 centimeters where now it's been, I think it's the same one. Yes, this is a triangulum galaxy. You can see this been coded red where it's moving away from us relative to the center of the galaxy. I mean, the whole galaxy is moving away from us because, you know, expansion of the universe, but this side of the galaxy is moving away from us a bit more, and this is moving away from us a bit less. So the whole thing is rotating. Let's see. There's often little holes in the center. This is not a good example of that, but you get these bubbles and frothy stuff that probably are where like supernova have gone off and made all this kind of interesting structure. I mean, this is the stuff that ultimately will turn into stars, right? It's going to have to turn into molecules of hydrogen first to be able to cool off enough to start collapsing into stars. So it's pretty cool. You can learn a lot about galaxies by studying the 21 centimeter line. So here's some more pictures. So yeah, so this is just an illustration of that point I was making, that the 21 centimeter is really interesting to see how galaxies interact with each other. So this is an optical, very old optical image of the M81 group. This is M81, which has a name, but I've forgotten what it is. Pretty galaxy. And it has these other two little neighbors. But if you look in 21 centimeter, if you look faint enough, you can see that they're all connected. They're all interacting. And you get the kinematics as well, right? So this is not just, I mean, I'm just showing you the pretty picture, but you can model the kinematics of this. You get like a three-dimensional view from the radio, which is pretty cool. And this is also demonstrating that hole in the center. So you often get these holes in the centers of galaxies, just because it's pretty. Here's another one of some nearby galaxies. This is actually this is a real map of our galaxy. We're inside it, so there's this bit that we can't see because it's on the other side of the Galactic Centre. But you can see the kind of spiral structure in our galaxy. This is what we think, you know, sort of the artist's impression of what we think it is, but this is real data. To the same linear scale, here's a bunch of other nearby galaxies. And my favorite one is this one, because it has a beautiful hole in the center, and this one has a strong bar, but that's by the way. It's not just external galaxies that we can detect this from, though. We can detect it in our galaxy, and actually you can do this with a relatively modest telescope. So this is one of the things that students in the last version of this class tried to do. So let me put you in the picture. So we're in the Milky Way, right? And we're rotating around the center of the Milky Way, and then everything else is as well, right? And so this is now an upside down version of that. So we're going to go this way. If you observe gas clouds at different places along a given line of sight, you're going to see clumps that have different recessional velocities just because of this rotation, right? So you see all these different clumps. So this is some real data of that. Now I'm showing it you as a scan with frequency, because that's how it's done. We basically scan the radio telescope along in frequency, and the Doppler effect means that those changes in frequency, if we associate them with 21 centimeter line emission, mean that you're observing something that's moving at a different velocity. So you will often see data that's 21 centimeter data presented in units of velocity, because you're basically saying what would be the velocity of 21 centimeter of something that emits 21 centimeter at this frequency. That makes sense? So you get these blobs and things. Okay, so this is now many sight lines. So think of each slice along this as a sight line with those ups and downs being where you detect stuff. And And you can read off this, the rotation of the galaxy, which I'm not going to get into in any great detail right now. The Ryden and Peterson, chapter 19, actually will talk about this. I think I made some of you calculate some of this as a homework assignment in 204 last year. But this can be done with a pretty modest sized telescope. Okay, so one more source of radio emission, and I want to just mention that there are other spectral lines. So there's other atomic lines, but there's also a whole pile of molecular lines. And so it turns out that molecular hydrogen doesn't do a lot because it's very symmetric. So molecular lines come from rotation and vibration of the chemical bonds between atoms in molecules. Anyone who's taken chemistry probably knows way more about this than I do. Hydrogen is very symmetric, so it doesn't really create very much in the way of emission of spectral lines. Molecules are bigger than atoms, but they're still in the quantum regime, right? So these things are quantized, so we still get very specific frequencies that excite molecules. And so one that makes some really useful lines for astronomy is carbon monoxide, which is not totally symmetric. So carbon and oxygen are not identical. This creates all kinds of lines. So some of these are carbon monoxide lines. Can we find them? There's so many lines. I can't see a carbon monoxide one, can you? This is a bad example. Anyway, all of these things that have like hydrogen, carbon, and oxygen, you can do all kinds of chemistry, basically, if you do this stuff. And different molecules trace different densities of gas clouds. So carbon monoxide is the one that we get excited about because it correlates pretty well with hydrogen, with molecular hydrogen. So people have like calibrated the relationship between carbon monoxide and molecular hydrogen. And so what you do is you measure how much carbon monoxide you can see, and you say, aha, so then I know there's this much molecular hydrogen. So anytime you see a molecular hydrogen map of a galaxy, it would have come from the CO observations. And then they have entire conferences where they argue about the calibration factor. But then there's all these other things like ammonia and different kinds of carbohydrates of different things that trace different density levels of the gas clouds. So that's quite cool. And you can kind of see them at different density levels. Okay, so that was it for my very brief tour of the sources of radio emission in the sky, in the night sky or the daytime sky for radio astronomy.